So now we're going to do that calculus derivation again, but this time graphically, right? I just want to show you one more time. You may have heard that the integral of a function is the area under the curve. You may have heard this before, right? And you may be thinking, I wonder if that's related to all this. So I'm going to show you, it is exactly related to all this. That is exactly what's going on. So if that last derivation made no sense, but you have some understanding of sort of the graphical version of calculus, like if that's all you left with after you took calc in high school or something, let me see if I can help here. So we're going to make the same drawing, position, velocity, and acceleration for something falling. And we're going to, again, make the positive direction up. I'm sorry, the positive direction down, just like we did before. So everything is positive here, right? And it's going to go like that. We know it does that. We know position, or velocity. Got to analyze these graphs. And this is a concept of calculus and kinematics. A concept of calculus would be this slope is increasing. Therefore, v must be increasing. And now, mathematically, you know why. Because xf minus xi was a times t. A times t is a constant. A is a constant. A times t is a line. Y equals mx plus b, right? So if it's just a times t, it's a line. So now you know why. And we're saying constant acceleration, right? Like that. Okay. So what I want you to think about is this. I'm going to write the phrase slope is the value, right? Because remember, the slope of the position time curve is the velocity. So we're going to draw something like this. To go this way, the slope is the value, right? Slope of position time is the velocity. The slope of velocity time, slope is value. The slope of the velocity time curve is acceleration, right? Look at it. Is the slope constant all the time and positive? Yes. The acceleration is constant and positive all the time. So the way I drew it, it all follows. But now that we've sort of talked about integrals, we can go the other way. And our phrase is that the area is the difference. Ooh, look at that. What does that mean? That means that if you pick two times, let's say ti and tf, and you draw like a, did somebody build their own Galilean ramp? Okay, no, I thought I heard bells. It's like, wow, you guys are like into this experiential learning stuff. So if you draw ti here and tf here, what this is telling you, area is difference. It means this area is equal to this difference here. The delta v is equal to this area, which is a times dt. You can almost see the integral, right? Delta v is the integral of a times dt. That'll give you the area. And you can do it again. You could say here, the area is the difference. Like that. And what does that mean? That means that here, this difference, the delta x, if we were to accelerate for this time, how far would we go? We would go from this initial x to that final x. We'd go that delta x. Right? According to these graphs, if we follow this trajectory, in a time ti, we're right here, we actually have an initial velocity, we would go to here. And we can figure out how far we go from all this information. Right? It's all geometry. Let's do it real fast. What would this be? Delta x would be x final minus x initial. And it would be this area under this curve right here. Right? That's what we just said. The area is the difference. So delta x equals this area. Equals area under VT curve, right? So that's just geometry. It's that area. Now what we're going to do is we're going to calculate that area, and it's like an asymmetric rhomboidroid, whatever it is. So we're going to divide it up into a triangle and a rectangle, like that. We just got to add up these two areas here. So you got a rectangle like that, and you got a triangle on top of it. Let's see. So let's see. Delta x is, I think I like to do the rectangle first, yes. What is the area of that rectangle? in the terms we've been talking about. Well, this side of the rectangle is delta t. What is this side of the rectangle that's special? It's vi. Right? It's the initial velocity. Okay, so there's the rectangle, vi times t. Well, delta t, I guess. We'll say delta t. Okay. Now, what's the area of a triangle? 1/2 base times height, right? 1/2 base times height. Plus 1/2, what's the base? Delta t. And what is the height? The height I'm going to write as, what is the height? The height of this triangle is the delta v. But what is the delta v? It's the area under here. What's the area under here? A times delta t. So here, this could be A times delta t again. All right, 1/2. This is the base, and together those are the height. Pure geometry, right? Have I done anything other than geometry here? No, I have not. I'm not even good at geometry. Let's see. So this is x final minus an x initial. So x final, I'll bring the x initial to the other side. And this is v initial t, and this is 1/2. I'm getting excited. A delta t squared. So it's the same thing, right? This is just the geometrical version of doing the calculus. Okay? So if you're like, how did that magic happen? It's right here. It's a triangle and a rectangle. Calculus is a triangle and a rectangle. Okay? That method could even work if A wasn't constant, but it was easy to do because A is constant, and we have a rectangle and a triangle. If A wasn't constant, you'd have curved things, and you'd have to do it. It'd be harder. Okay? Now, I'm talking to a bunch of future doctors and pre-meds, right? So I got to tell you why I need you to know this information. Where's my slide? Did I delete the most important slide in the whole thing? Oh, here it is. I don't know how it... Oh, yeah, Elon was second. Okay, this is a paper published in 1996 in the journal Diabetes by a medical doctor in the Texas Medical Center. I know 1976 sounds like a long time ago to you. It's not that long ago, okay? Trust me, it's not that long ago. I was older than you, but it wasn't that long ago. And it was centuries after calculus was invented. And this actually had this idea that, when you measure the glucose in the blood of a diabetes patient, it might vary in time. And they had this brilliant idea that we could get the total dose of glucose by coming up with a mathematical model to determine the total area under the glucose tolerance and other metabolic curves. Okay, I'm blocking this person's name to protect their identity, but they said all we got to do is draw little trapezoids under the curve and add them up and make this mathematical model, and we get the total dose, right? So they reinvented calculus. Okay, this is called the trapezoidal rule. You may have seen this in Calculus 1. It was rediscovered in 1996 after being lost for 5 minutes in this person's mind. Okay, but what's amazing to me is if you know how scientific publishing works, they had this idea, they wrote the whole paper, and it never occurred to them that, oh, this is calculus. They submitted it. It was looked at by an editor of this journal who said, oh, that's pretty cool. Let me send that out to referees. Okay, referees got it and said, hey, I like this. Right, so at least 5 MDs looked at this and said, this should be published in Diabetes, right? And it got published in Diabetes. And I protect their name because they named it after themselves, okay? It was so-and-so's method, and they dedicated it to their parents. Oh, it's brutal. It's brutal. And there was a letter to the editor in the next edition, and it was a one-sentence letter, and it said, so-and-so's method is the trapezoidal rule. And that was the whole thing. So this still gets cited, though. Okay, so when you are all doctors and bioscientists, if you go out in the world, do not embarrass me, please, okay? Know what calculus is. Don't forget what calculus is, please.